Algebra 1 Lesson 66, and we'll look at 67. But first, Lesson 66, we are looking at solving inequalities by adding or subtracting. So in order to solve our inequalities, sometimes we have a variable with an operation, like x minus 10 is less than 6. But if I want to graph this, I first need to solve for my variable, just like we would with any equation. Then we can graph it more effectively. So just like we would with an equation, I want to do the opposite in order to get x by itself. So if I have minus 10, I want to do the opposite of that, so plus 10, in order to get x by itself, and we get x is less than 16. And like we've seen in previous lessons, we will graph this by saying if I have a less than symbol, that's going to show itself as an open dot on the number line. Now if I want the numbers less than 16, I'm going to have an arrow pointing to the left. Okay, let's try another one. If we have x minus 8 is greater than negative 4, well, just like we did before, we're going to do the opposite and add 8. And I get that x is greater than 4. So I'm going to put some numbers on my number line. I have an open dot on 4 going to the right because I want the numbers that are greater than 4. All right, again, now we have x minus 3 is greater than or equal to 5. So we add 3 to each side and get x needs to be greater than or equal to 8. So if I have my numbers, it's going to now be a closed dot on 8 because it's greater than or equal to, because we can have 8, and going to the right because I want the ones that are greater than. Same idea, we're going to add 2 to each side. We get x is less than or equal to 5, so closed dot on 5, going to the left. Now a couple situations. An airline allows a suitcase that weighs no more than 50 pounds when it's full. Jared's empty suitcase weighs 5 pounds. How much weight can Jared pack in his suitcase? Write an inequality to solve the problem. Well, what we're saying is if we have this suitcase, which is already 5 pounds, he's going to add to that a certain amount of weight, but we know that overall that needs to be less than or equal to 50, because that's the limit on the airplane. So in order to solve this, we're going to subtract 5 and get that x needs to be less than or equal to 45. So that when we graph it, we're going to have a closed dot on 45 going to the left. And of course, we would have an endpoint at 0 technically, but when we're just looking at this inequality, we will just point it to the left, showing that he can have all of those different weights in his suitcase up until that amount of 45. And last example in lesson 66, Michael's horse can carry no more than 200 pounds on its back. If Michael weighs 168 pounds, how much can his saddle weigh? Okay, so we know that Michael is 168. But we don't know all of the different amounts that his saddle could be up into this amount of 200. So just like the other one, we can subtract 168 and get that x is less than or equal to 32. So once again, we would put a closed dot on 32 going to the left. Okay, so that's lesson 66. Lesson 67. We are solving and classifying special systems of linear equations. So your goal for this, we need to be able to classify them in 3 different areas, basically. One we will call consistent and independent. One we will call consistent and dependent. And the last one is inconsistent. So some vocab terms here. Inconsistent, we have no common solution. These are our parallel lines because if we have a system, then there is no solution when they are parallel. Dependent systems, they have an infinite number of solutions, which we can also say are dependent equations. They have the exact same solution set. The equations are the same. So if I were to graph one, the other one would be right on top of it. We have the same line. So there's an infinite number of solutions. Consistent means that there's at least one solution. There just has to be one. There could be one, there could be a million. There just needs to be one for it to be consistent. Independent has exactly one. These are our lines that intersect at just one point. Okay, these are most typical systems of equations. So let's first look at inconsistent systems. So this is when no common solution exists. So we need to solve these inconsistent equations. And like we've done in the past, we could use substitution here to say if y equals 3x, I'm going to plug in this 3x where I see it in the other equation. And what ends up happening is we see, okay, if I plug that in, I have negative 3x plus 3x is equal to negative 4. Well, negative 3x plus 3x is just 0, and 0 equals negative 4? No, that's not true. Okay, so just like we would solve an equation, we would say 0 does not equal negative 4. No solution exists. And that is because these are parallel. If we were to get both of these into slope-intercept form, I would add 3x to each side and see that y is equal to 3x minus 4. That means we have the same slope in each equation but different y-intercepts. Okay, so these are actually parallel lines. So yes, these are inconsistent, no common solution exists, because they will never cross, they will never touch, they are parallel. Okay, let's try another one. So just like the other one, we're going to plug this in and get 5x equals 5x plus 6. Well, we can subtract 5x on each side. And we get 0 is equal to 6. Well, that's not true, so we have no solution. We could have also seen from the original equations, we have a slope of 5 in each of them, but we have a different y-intercept. So yes, these are parallel. There is no solution. So we call these inconsistent equations. Our next type is dependent systems of equations. So dependent systems have an infinite number of solutions, meaning if it's on one line, it must be on the other, okay? And we can do that an infinite amount of times, which means we just have the exact same equation. So one way to determine if a system of equations is dependent, we want to write these equations in slope-intercept form. So in order to do this, for the first one, we are going to subtract x from each side, and then we're going to divide by 3. And we see that when we divide by 3, I get negative 1/3 x plus 2. Well, that's exactly the same as when we subtract 1/3 x from each side on the second one, we get minus 1/3 x plus 2. These are the exact same equation. So even if x is 2, or let's say if x is 3, then I get y is 1. In the second equation, x is 3, y is 1. We can do that an infinite amount of times. So these are called dependent systems. Okay, the second way to solve these to decide if it's dependent is to use one of our methods like graphing or substitution or elimination to solve this system. So in this case, I would need to get one of these variables by itself. Okay, so I end up getting y alone in the first equation, and that is 1/4 x minus 2. You could have also gotten x alone. It doesn't actually matter. But we get y alone, and we get 1/4 x minus 2. I plug that in for y right here, so that I have 1/4 x, my original in that equation, minus this quantity. So we're going to minus the 1/4 x and minus the negative 2. So that we get 1/4 x minus 1/4 x plus 2 equals 2. Well, as you can see, these x's end up canceling out, and we end up with 2 equals 2. Since that is a true statement, this has infinitely many solutions. They are dependent. Okay? So when we review a little bit on these two types that we have inconsistent, we're going to get, so I'll write it out. If we have inconsistent solution or inconsistent system, we are going to get answers to our system. Well, of course, they're going to be parallel. And we are going to get solutions like 0 equals -4, or 2 equals 3, or 5 equals 26. Okay, we're going to get solutions that are not true. With dependent systems, we are going to get solutions like 2 equals 2, or -10 is equal to -10, or x is equal to x, or even 10x is equal to 10x. We are going to get true statements, okay, that regardless of what number we put in for our variable will always be true. And these are our dependent. These are the same line. So those two plus my typical system of equations are 3 different types. So number 1, we have my consistent and independent. Remember that consistent means that it has at least one solution. Dependent means it has exactly one solution. Okay, so these are consistent and independent when we have our solution, when we have our intersection for these two lines. Consistent and dependent, those are the same line. Okay, consistent meaning we have at least one. Dependent means we have infinitely many. So we have one line. And inconsistent, we don't have a solution because they are parallel. Okay, so let's decide what we have here. So the first one, we are given x minus 1/4 y is equal to 3/4, and 2x plus y is equal to 1. Well, let's go ahead and substitute to see what happens. So let's say we get y by itself in this one. So we have y equals -2x plus 1. And I'm going to plug that information into the other equation where I see y. So I'm going to get x minus 1/4 times -2x plus 1. And that equals 3/4. I'm going to expand and get x plus 1/2 x minus 1/4 is equal to 3/4. I'm going to combine like terms here and get 3/2 x. And I'm also going to do this same step. I'm going to add 1/4 to each side. So I'm going to get equals 1. And to get rid of that 3/2, I'm going to multiply by the reciprocal, 2/3. Which means x is equal to 2/3, meaning if I have an x actually giving me a number, that means that I am going to get a y value once I plug it back in, and I have a consistent and independent system because we will actually have a intersection point when I graph these lines. Okay, so when we actually get a value for x and y, we will have a consistent and independent system. And you can practice graphing these. Remember, if you graph them on your graphing calculator, you will have to transform them into slope-intercept form. So make sure that you're doing that. Or you could use our methods, so with standard form, basically, in order to find the intercepts and graph. Okay, so another one. 3x plus y is equal to 2. Well, let's see. This almost looks like it could be parallel. They have very similar possible slopes. So I'm going to see what kind of lines these look like. So I'll subtract -3x from each side, and I get y is equal to -3x plus 2. And here I have y equals -3x minus 4, meaning they have the same slope of -3, but a different y-intercept, so these are inconsistent. Okay, because they do not have a solution. They are parallel. Okay, another one. Here, let's see. I am going to, let's solve for y and see, are these consistent? Are these independent? Are these dependent or inconsistent? Let's see. So I'm going to solve for y in each of these cases. So I'm going to subtract x. And I'm going to get -7y is equal to 3 minus x. Divide by -7. And I'm going to get y is equal to, I'll flip it so I have x first, minus x and minus 7, so I have a positive 1/7 x minus 3/7. And then I'll do the other one. I flipped the 2x to the other side by subtraction, so I have negative 5y is equal to negative 2x plus 15, divide by negative 5, and I get y is equal to 2/5 x, a positive, minus 3. So when I look at these, they're definitely not the same equation. They don't have the same slope, so they couldn't be parallel, so these must be consistent and independent. And we could prove that by truly finding the solution, in this case by substitution, by saying I'm going to equal these to each other and get 1/7 x minus 3/7 is equal to 2/5 x minus 3. We can go ahead and find x, plug it in, find y. All right, another one. Determine what the system is. Okay, well, let's say I want to use substitution right away. I'm going to take this information and plug it in for y. Get 8x minus 5 times 4x minus 5. That equals 16. So I'm going to expand to get 8x minus 20x plus 25 equals 16. Combine like terms and we get negative 12x, and I'll subtract 25 on each side, equals a negative 9, so x equals 3/4. Which means if I have a value for x, these are consistent and independent, because I could plug it back in, find our y value, meaning we have one and only one solution. All right. Brandon started jogging at a rate of 4 miles per hour. After he jogged 1 mile, his friend Anton started jogging on the same path at a pace of 4 miles per hour. If they continue to jog at the same rate, will Anton ever catch up to Brandon? Well, logically, we would say no. They're going at the same speed, and Brandon started earlier, so he's a mile ahead. Which means if I write an equation for him, I would say his total distance equals 4 miles per hour plus the 1 mile he already has. And then I could describe Anton by saying y equals 4x and then plus nothing, because he started after Brandon. Looking at these, we can see they have the same slope, different y-intercepts, so these would be inconsistent. Okay, they are parallel. They are running basically parallel to each other the entire time. They will never meet. All right, and I think this is our last example here. Hannah and her mother are going on a bike ride. Hannah's mother leaves the house traveling 13 miles per hour. Hannah leaves the house after her mother has biked 2 miles and tries to catch up to her by traveling 17 miles per hour. Will she catch up with her mom? So let's write an equation for once Hannah starts, where is everybody? So we would say her mother's miles is 13 miles per hour plus the 2 that she's already biked. And Hannah would be 17 miles per hour plus nothing because she just started. And in this case, we would say, yeah, we will be able to get a solution here because they're not parallel and they are not the exact same line, so we will have a solution. And we could substitute this information in here, saying 17x equals 13x plus 2, and we subtract 13x from each side and get 4x is equal to 2, so x is equal to 0.5, meaning after half an hour, she will catch up. After that half an hour, they will both be at, let's see, if I plug it in to the second equation, 0.5 times 17 will give us 8.5. Okay, so after half an hour, they will both be at 8.5 miles. Well, I hope this is helpful for your homework and for studying.